witness the physical reality of these invisible highways, we must turn our attention to the specific, tangible discoveries that have transformed the cosmic web from a theoretical construct into an observational certainty. For decades, the filaments were ghosts in the machine, lines drawn by computer algorithms connecting the bright dots of galaxy clusters. But in 2012, a team of astronomers achieved something remarkable. They captured the shadow of a filament itself between the two massive galaxy clusters, Able 222 and Able 223, separated by some 40 million light-years, lies a bridge to the optical telescopes that scan the sky. The space between these clusters appeared largely empty, a void sprinkled with a few wayward galaxies. But when the astronomers applied the technique of weak gravitational lensing, analyzing the subtle distortions of the background light, the ghost revealed its shape. They found a massive ridge of dark matter connecting the two clusters, a dense, thick cord of invisible mass containing more material than the clusters themselves. This was the first robust detection of a dark matter filament, a physical confirmation that the clusters are not isolated islands, but are nodes in a continuous, flowing geography. The dark matter in this bridge is not stagnant. It is a conduit. We must imagine the gravitational potential of this filament as a deep valley in the fabric of space-time, a trough along which matter, both dark and visible, slides. The galaxies caught in this trough are like beads sliding down a string, accelerating toward the clusters at either end, driven by the relentless pull of the nodes. This journey along the filaments is not without consequence for the galaxies themselves. The drift is a transformative process, a passage that alters the destiny of the travelers. As galaxies move from the lonely, low-density voids into the denser environment of the filaments, and eventually into the chaotic hearts of the clusters, they undergo a metamorphosis, often described with a somber biological analogy. They die. Astronomers categorize galaxies into two broad color camps. The blue cloud, consisting of active, spiral galaxies rich in gas and newborn stars, and the red sequence, populated by elliptical, gas-poor galaxies where star formation has ceased. The transition from blue to red is the transition from life to stellar death, and the cosmic web is the killing floor. As a blue spiral galaxy drifts along a dark matter filament and approaches a massive cluster, it encounters the hot, tenuous gas that permeates the structure, the intracluster medium. The galaxy, moving at thousands of kilometers per second, plows through this stationary gas. The resulting wind is fierce, acting like a cosmic leaf blower that strips the galaxy of its own internal gas, the fuel for future stars. This process, known as ram pressure stripping, effectively strangles the galaxy. The dark matter plays the role of the trap. Its gravity accelerates the galaxy to the high speeds necessary for this stripping to occur, and its deep potential well holds the hot gas in place, creating the resistive medium. We see the aftermath of this violence in jellyfish galaxies. Objects that exhibit long tentacles of stripped gas trailing behind them, glowing with the light of young stars formed in the wake of the destruction. These tentacles trace the path of the galaxy through the dark matter halo, marking its trajectory as it falls. Eventually, the galaxy is drained. It loses its spiral arms. Its blue hue fades to a dull red as the massive, short-lived stars die out, leaving only the long-lived, cool dwarfs. It settles into the center of the cluster, joining the swarm of other red and dead ellipticals. A graveyard of galaxies bound forever by the gravity of the dark node. Thus, the drift through the cosmic web is a journey of maturation and eventual obsolescence, a cosmic aging process dictated by the density of the dark environment. To fully appreciate the scope of this drift, we must look even further back, past the formation of the current web, to the epoch known as the cosmic dawn. Before there were stars to strip, before there were galaxies to quench, there was only the dark. About 100 million years after the Big Bang, the universe was dark, filled with neutral hydrogen gas and the slowly collapsing halos of dark matter. These first halos, much smaller than the Milky Way, mere mini-halos, were the incubators of the first light. In the silence of the dark ages, the neutral hydrogen fell into these mini-halos, cooling and condensing until the pressure ignited the very first generation of stars, the population Roman 3 stars. These were monsters, hundreds of times more massive than our sun, burning with a ferocious ultraviolet intensity. They were the first lighthouses in the dark ocean. The structure of the dark matter determined where these lights would turn on. The first stars did not appear randomly. They appeared in the highest peaks of the dark matter density field. The drift of baryons into these primordial dark wells ended the cosmic dark ages, initiating the epoch of reionization, where the ultraviolet light from the first stars and quasars began to burn away the neutral fog of hydrogen, rendering the universe transparent. We are on the verge of mapping this ancient era with radio telescopes like the Square Kilometer Array, SKA. These instruments will look for the 21 centimeter line, a specific radio wavelength emitted by neutral hydrogen. By mapping the intensity of this signal across the sky, we will be able to see the Swiss cheese structure of reionization, bubbles of ionized, transparent space growing around the first dark matter halos, expanding and merging until the fog was cleared. This map will effectively be a map of the dark matter skeleton as it existed 13 billion years ago, the earliest blueprint of the web. Yet, even as we build this consistent, triumphant narrative of cold, dark matter, we must acknowledge the persistent whisper of dissent, the scientific tension that keeps the field honest. There exists a small but vocal contingency of physicists who argue that the dark sector is an illusion, a phantom created by our misunderstanding of gravity itself. This hypothesis, known as Modified Newtonian Dynamics, MOND, suggests that there is no invisible matter, but rather that the laws of gravity change at extremely low accelerations, such as those found in the outer rims of galaxies. MOND can eerily reproduce the rotation curves of spiral galaxies without a single ounce of dark matter, simply by tweaking the equations of Newton and Einstein. It is an elegant mathematical solution that removes the need for a ghost. However, MOND struggles to explain the universe on the largest scales. It falters when faced with the cosmic microwave background, and it cannot easily account for the bullet cluster, where the gravitational lensing clearly separates from the visible matter, the drift of the dark matter, as evidenced by the large-scale web and the separation of mass in collisions, remains the most robust explanation we have. The majority of evidence points not to a modification of the laws, but to the existence of the stuff, the substance, the cold fluid that fills the dark. This substance, while invisible, acts as a lens for the entire universe. The cosmic microwave background, CMB, the afterglow of the Big Bang, must travel for 13.8 billion years to reach our detectors. As it travels, it passes through the evolving cosmic web, through the filaments and the growing clusters. The gravity of these dark matter structures bends the path of the CMB photons, slightly distorting the pattern of hot and cold spots. This phenomenon, known as CMB lensing, allows us to create a map of all the mass in the visible universe, integrated along the line of sight. The Planck satellite has produced such a map, a modeled sphere that looks like a dirty window. This dirt is the dark matter. By cleaning the window, by analyzing the statistical properties of the distortions, we have confirmed that the web is there, extending all the way back to the surface of last scattering. We see the potential wells of the dark matter deep in the past, and we see how they have grown. The agreement between the predicted growth of dark matter structure and the observed lensing map is one of the triumphs of modern cosmology, a confirmation that our model of the slow, cold drift is correct to an astonishing degree of precision. Let us descend again from the cosmic scale to the intimate physics of the halo. We must consider the substructure crisis in more detail. If dark matter is truly cold and collisionless, the Milky Way should be swarming with thousands of tiny, dark clumps, the failed seeds of galaxies. We call these dark matter clumps, or subhalos. While we have found some faint satellite galaxies, many subhalos should be completely dark, having never managed to attract enough gas to form stars. These invisible prowlers drift through our galactic neighborhood, unseen, but perhaps not unfelt. It has been proposed that the gravitational influence of a passing dark subhalo could disturb the delicate disk of our galaxy, causing ripples and warps. Some astronomers analyze the vertical motion of stars in the Milky Way's disk, looking for the breathing mode or bending mode oscillations that would signal a recent flyby of a dark object. We are checking the seismology of the galaxy for the footsteps of ghosts. Furthermore, these dark clumps might act as lenses on a microscale. If a dark subhalo passes in front of a distant star, its gravity will momentarily brighten the star, a phenomenon called microlensing. Surveys watching millions of stars in the Magellanic Clouds or the galactic bulge are hunting for these brief flickers. It is a search for the invisible needle in the haystack of light. If we find them, if we can prove that the halo is grainy and full of lumps rather than smooth, we will have validated the cold, dark matter model. If the halo proves to be smooth, we may have to embrace warmer or more exotic forms of dark matter, implying that the ghost is more ethereal than we thought. There is also the question of dark matter annihilation. In some theories, particularly those involving WIMPs, dark matter is its own antiparticle. When two dark matter particles collide in the dense center of a galaxy or a cluster, they should annihilate each other, releasing a burst of energy in the form of gamma rays. Telescopes, like the Fermi Gamma Ray Space Telescope, have been staring at the centers of the Milky Way and nearby dwarf galaxies, looking for this excess radiation, a glow that cannot be explained by pulsars or black holes. There have been hints, an unexpected galactic center excess of gamma rays that initially caused a wave of excitement. Was this the signal of the dark matter drift consuming itself? The debate rages on. Some argue it is indeed the signature of dark matter. Others contend it is merely a population of unresolved millisecond pulsars, spinning neutron stars that mimic the signal. The thermal signature of the drift is still ambiguous, a warm spot in the data that refuses to resolve into a clear picture. The complexity of the cosmic web is also a story of hydrodynamics, the physics of fluids. The ordinary matter, the gas, does not just passively follow the dark matter, it pushes back. We must imagine the cosmic web not just as a gravitational skeleton, but as a system of feedback. When a supermassive black hole at the center of a galaxy cluster erupts, it launches jets of plasma near the speed of light. These jets inflate massive bubbles in the hot intracluster medium, shock waves that ripple out for hundreds of thousands of light years. These outbursts inject energy into the surrounding environment, preventing the gas from cooling and falling further into the dark matter well. This stops star formation. It keeps the galaxy red and dead. The black hole, a speck compared to the size of the cluster, regulates the growth of the entire system. It is a feedback loop connecting the smallest scales, the event horizon, to the largest scales, the dark matter halo. The drift of the gas is arrested by the fury of the central engine. Simulations that include this AGN feedback, active galactic nucleus feedback, produce galaxies that look much more like the real universe than simulations that only include gravity. The dark matter builds the stage, but the black holes dictate the lighting and the mood of the play. As we ponder the future of this research, we must look to the next generation of maps. The Euclid mission, launched by the European Space Agency, and the upcoming Nancy Grace Roman Space Telescope by NASA, are designed to conduct tomography of the universe. They will slice the cosmos into time shells, measuring the distribution of dark matter at different epochs. This will allow us to make a movie of the drift. We will see empirically how the web tightened over time. We will measure the growth rate of structure, a parameter that tells us how fast gravity is pulling things together versus how fast dark energy is pushing them apart. If the growth rate deviates from our predictions, it could signal a breakdown of general relativity on cosmic scales, a hint that gravity itself is more complex than Einstein dreamed. The study of dark matter is, in essence, the study of humility. We are the minority, the atoms in our bodies, the rock of the earth, the plasma of the sun. This is the exotic matter. The normal state of the universe is dark, cold, and invisible. We are the rare, glowing anomalies, the bioluminescence on the surface of the deep sea. The drift of the dark matter is the primary motion of reality. Our movements, our orbits, our galactic rotations are merely the secondary responses to that great, unseen current. To understand the web is to understand our place. We are residents of a small, glowing node, drifting along a filament of shadow, caught in a gravitational tide that began before the first star ignited and will continue long after the last star fades. In the final segment of this narrative, we will turn our eyes to the ultimate fate of the web. We will explore the theoretical end states of the universe, the big freeze, the big rip, or the vacuum decay, and how dark matter dictates these scenarios. We will summarize the grand journey we have taken, from the initial density fluctuations to the vast superclusters. And we will close with a meditation on the philosophical implications of living in a universe where the most important substance is one we cannot see. The drift continues, carrying us toward an uncertain but magnificent future.